Okay, well, let's get started. It's my pleasure to introduce Sasha Tchekhovskoy, who's coming to us just from not so far away. So Sasha did his undergrad at Moscow Institute of Physics and Technology.
Yes.
Okay. Then he did his PhD at Harvard with Ramesh Narayan. Then he did a postdoc at Princeton, the Princeton Center for Theoretical Sciences.
You know that one, though.
Where I was also a postdoc. So Sasha told me that I should go there because he had a good time. He was also an Einstein Fellow there. And then afterwards, he went to Berkeley for a couple of years, and that's where we met. He was a postdoc there while I was a grad student. And then after Berkeley, he came here and is in the physics and astronomy department. And I think just last year, Sasha received tenure, so is now an associate professor.
Yes,
So
you can think of it as, after 6 years of PhD, you get to the next level. So
yeah. So so Sasha is an expert in astrophysical fluid dynamics. He studies flows around black holes and other compact objects. And he's also involved in some numerical development. So he has a GPU accelerated code, which he's going to show us some of the results from today, called Hammer. And I'm excited to hear about a black hole burps and fireworks. So take it away.
Thank you so much.
Let's thank Sasha for
Thank you so much for having me here. I'm so happy to see so many familiar faces, and I'm glad that it took only 8 years for me to give a talk here, Daniel. I am a black hole dietologist. So the 5-year-old version of what I do is I take a black hole, put it inside of a computer, close the door so it doesn't get out, and then give it some food to graze on. And then when I infuse this food with magnetic spice, the black hole gets activated. It starts burping away the surroundings, including the food itself. And that's the process I'm really interested in studying, as we can, talk to observers, look at the black holes telescopes, and then try and figure out what the black hole ate by matching the burping that we see in the simulations and observations. So what is my talk going to be about? I'm going to be mostly interested in finding the most optimal diet, because when the black hole gets activated, the burping happens by black holes that eat from these whirlpools of gas called accretion disks. And then if magnetic fields get on the black hole, then they can coil up those can get coiled up by the rotation of the black hole and produces magnetic springs. I will explain more in detail, that are called jets. And this is how black holes can blow up or burp away their surroundings. So I'm interested in figuring out what's the right diet for the black hole to produce these jets. More specifically, if we invest a certain amount of energy, mc squared, into the black hole, or converting it to a rate m dot c squared into a black hole, what is the rate of energy that these jets carry? And more importantly, what are the conditions for these jets to happen in the first place? And how these jets, blow away the surroundings. If there is a supermassive black hole at our galactic center, we better know why it is quiet, because if it gets active, maybe we'll be in trouble. Finally, because the jets blow away the gas that the black hole eats in the first place, how does this cycle, feedback cycle, as we call it, feedback loop, affects the amount of food or mass that the black hole has access to in the first place? So, let me give you some visual stimulation here. It's early morning. Let's look at pretty pictures. So this is an X-ray image, and pretty old X-ray image taken by the Chandra X-ray telescope, whose funding right now is in jeopardy. So if you're have any say anywhere, if you want more of these pretty pictures, please speak up. there are prettier pictures as of late, but I really like this one because this one is really when we first realized that what we're seeing in front of us is a black hole literally burping away the surroundings. So if we do the sort of astronomical version of Adobe Photoshop, image sharpening, then we will see that, there are these sort of cavities that the black hole appears to blow out. And there are these sort of wisps, concentric wisps that seem to be originating at the center that presumably carry black hole energy and energize the surroundings. And there are more examples like that. For instance, this is M87 black hole. And you can see more of the same examples, the shocks, so waves over here. There are cavities blown up by the black hole. And these are the jets themselves. And this is perhaps the most dramatic example of this black hole feedback, where the black hole affects its own food supply. Here in blue, we see thermally produced X-ray emission. Optical UV light, let's say 1 electron volt. This thing is 1 kilo electron volt. So this is not something that you can easily get in your oven. So blue is really not blue, but X-rays. And purple, pinkish, not quite Northwestern color, but still, shows the radio emission from really, really energetic electrons that are going around magnetic field lines, which are filling this space. So this is called synchrotron emission. And what you can see here is that where there is a synchrotron emission, there is a decrement, there is a hole in the blue emission. So that means that the heavy gas has been pushed away by whatever this is. Maybe I should be pointing on my screen so that remote people can see. But whatever this is, the gas was pushed away. And so that means that this burp that the black hole produced over here, these jets, they had to displace the heavy gas, had to inflate this sort of balloon cavity inflated by whatever this is. And we think it's a mixture of, magnetic fields and hot plasma. And if we estimate the amount of work that's needed to inflate this, like if I were to start inflating a balloon, imagine a virtual balloon here, I get out of breath because I need to go to the gym and I don't. But you would no problem be able to inflate the balloon. So the black hole has to do work because I am getting out of breath because I'm doing work to inflate the balloon. That's why the black hole has to do work as well. And we can estimate that PdV work, and it turns out that this energy that's been invested here is comparable. Maybe it's on the order of 10% of the entire rotational energy of the black hole if it were spinning at the maximum rate. So what that means is that there is, some magical stick that presumably exists, that somebody comes with a stick, sticks it into the black hole, slows its rotational speed down, and extracts a bunch of energy and dumps it into the surroundings. So what I will argue is that the stick is magnetic fields, and that's what I'm going to be talking about next. Are there any questions at this point? Feel free to interrupt me. It's totally okay. I really like it to be interactive.
I have a silly question.
Yeah.
So what causes the jets?
Oh, I'm really glad that, we had this discussion before the talk where I said, this is a list of questions that you please ask. So, oh, I wasn't supposed to say that. Perfect. I have my people here. All right. So what causes the jets? It's a perfect question. Indeed, what causes the jets? And when I got into the field, I just couldn't understand, why would they be so collimated? It seems like it's a conspiracy. Gas falls in the equator, sure, there will be some outflow maybe, but why would it be so collimated? That's ridiculous. And how can magnetic fields extract the energy from anything? That sounds even more ridiculous. So let me cook up this is applied math department, right? Engineering sciences and applied math department. And so, although I'm not an engineer, but if we wanted to sort of set up an experiment inside of a computer, then this is what I would do. I would, place the central object, be it a black hole or a neutron star, or a white dwarf, or like a regular star like the sun, or maybe a star that's just forming. More exciting, more action. What matters is that it is magnetized, so there is a magnetic field line sticking from outside out of it. And because we will say that this object is highly conducting, it means that if its surface moves, magnetic field will also move with it. We call it magnetic flux freezing condition. You can think of it as, who took coffee or tea this morning? Coffee or tea? About half. Wow, you people are strong. Petra, you didn't take coffee or tea? Oh, you did? Okay. I got worried for a second. I have some I can share. Who takes milk with your coffee or tea? Oh, fewer people, but still, okay. People in the front row, yes, see, like take milk, clearly you'll be sitting in the front row. Right, so when I mix and you mix milk into your coffee, then wherever the coffee goes, that's where the milk goes, right? So that's the way you can think about flux freezing, except it goes both ways. If you take the milk and mix it, the coffee will go there as well. So basically, wherever the magnetic fields go, that's where the gas goes. Wherever the gas goes, magnetic fields go as well. So magnetic fields can dominate, like in this case, and take the gas wherever they want. Or if gas dominates, it will take the magnetic fields wherever they want. So it's really a coupled system. So if we then follow this magnetic field line out, it will probably connect to some gas. So I will represent the gas as a ceiling over here. This is a ceiling. And so it's also highly conductive. So the other end of the magnetic field line will be attached to the ceiling. So that one is fixed. And then the foot point of the field line will rotate together with the central object, like a star rotates, a neutron star rotates, a black hole rotates. And let's wait for n rotations of this central object. And what you're going to see is that initially vertical magnetic field line will become twisted into a helical structure or a magnetic spring. And there will be one loop per each rotation. So here there were 1, 2, 3, 4, 5 loops. Okay. If we continue waiting, and there will be more and more magnetic loops twisted by the rotation of the central object, then the density of these loops increases. The density of the loops is the strength of the magnetic field, toroidal magnetic field, B phi. And that magnetic field applies pressure given by the formula that we learned from high school. Do people in this country learn this formula in high school? No? Oh, no. Okay, college. All right.
College, that's cool.
Oh, no. Okay, the B phi. I mean, but with the epsilons, do you learn it in high school? No?
No.
Okay. All right, we need to change that. All right, so B phi squared over 8 pi, that's the pressure that the poor ceiling will receive. And eventually it will get out of control because the number of loops keeps increasing linearly with time, and the ceiling will give in. In other words, our jet will push through the surroundings, drill a hole through, and what we will have is that magnetic spring that we've so carefully twisted will just punch through the whole thing. It literally behaves just like a spring with some complications. Yes.
So the ceiling that you've drawn here is the clouds that are like in the images?
You can think of it this way.
Okay.
Yeah, but we're looking at such large scale, so eventually that gas will get down to the black hole. It will be shrouded by stuff. And then if this magnetic field is strong enough, then it will be able to push that thing away. Actually, it's not a given that every time you have this cloud of gas feeding the black hole, the jet can be produced.
But this is the length scale that was sort of on those images.
No. That length scale, like it's like way, like millions of times larger than this scale. So we don't really see that deep on those images. But there are other ones where we actually see these scales. I don't think I'm showing those, but I can try and dig it out. Any other questions? Yeah.
So you said that there's a linear increase. Why is there not like a saturation?
Great questions. Awesome audience. There will be saturation eventually. I just didn't want to get there. Yeah, I'm trying to simplify this. This is a 10-year-old version. My introduction was 5-year-old, so I'm going up in age. It's a complicated thing. I don't want to get in there, but you're absolutely right. Eventually there will be saturation because the field will start slipping through the black hole and then it won't be doing too well. Exactly right. But when you have neutron star, for instance, then it's a different story because it actually is really frozen, and there the saturation will happen because this whole thing will be unstable. It will just start falling apart, reconnecting. It's like if you take a spring and you take it out of a pen, right, and then you try to squeeze it. What happens to it? Buckles, exactly. Flies to the side, and that's exactly what happens here. That's called a magnetic kink instability. That will basically break the conductivity and cause the magnetic fields to reconnect away and heat everything up. So that's how the saturation happens in general. Any other? Yeah.
No, if it breaks through, kind of sends this sealing away, then it relaxes, right?
Correct.
And so that will allow again for matter to come in and the new sealing to be formed and the entire thing to restart.
It's actually not somebody. Oh, sorry, I interrupted you.
I was going to say if this is not kind of continuously, there is kind of a periodicity.
So I think we can come up with scenarios where exactly what you envision will happen. Typically, however, what happens is once a channel has been drilled, then that is an escape channel. So the lid was taken off. And so as long as there is no major downfall of gas that will close this channel and will put the lid back, then you can think of the sort of steady state. What I'm going to be showing you in the simulations is the following. So we still have the original magnetic field line that's continuously reprocessed by the rotation into these hoops or toroidal field loops of the magnetic field that emanate at a certain rate. That's steady state rate. They slide up the original magnetic field lines, and as they do so, they expand sideways, and therefore the pressure here is becoming lower than it was before because there is more area for the field to expand to. So there is a pressure gradient that pushes these loops out. Okay, so that's how these loops get accelerated. And if there is any plasma attached to these loops, if it's not too much mass, then this plasma can be accelerated to speeds close to the speed of light, like literally 99.999% of the speed of light. We see that observationally. And the reason for this is that the jets are, on the one hand, connected to the black hole, which sucks everything in. On the other hand, they open up to infinity, and there is no gas that can cross due to flux freezing condition from the outside. And so this becomes really, really clean. Not maybe cleaner than the cleanest lab on Earth. Maybe not. Actually, I'm not so sure, but we can talk about it. I'm really bad at engineering, so I would like to know. So because there is such a scarcity of matter here, the magnetic energy dominates over rest mass energy by factors of 100 or something like this. So B squared over rho C squared, where rho is the mass density, becomes of order 100 or more. And therefore, this plasma can accelerate to Lorentz factors that measure the speed when it's close to the speed of light, to of order 100 or more. So that's it's a bit technical, but does that answer your question? So this channel kind of stays there if the ambient medium doesn't dramatically change things. Any other questions?
Do you run out of matter? I mean, if the densities you are accelerating and sending it and you have no way for particles to get in, at some point there is nothing to be ejected. So what do you see
This is kind of the point that I'm going to get to. So, I mean, of course, we discussed about asking this question, but a little bit later in the talk. Okay, so
sorry.
No. But no, that's exactly the right thing. That's exactly what I want you to have in your mind. So thank you for asking this question is, so if this energy injected, so you can kind of see energy will go upward. Energy goes upward, but the mass can still fall sideways. And so can this energy even couple to the mass that comes sideways? I mean, that's the question. And how efficiently can it do that? Make sense? Okay, so let me get to the simulations directly. This is a movie that is maybe 5 years old now. 5 years old. And I kind of lied to you at the beginning that said I really want to have jets happen. But it turned out, I will show you that it's actually, once they happen, there's no way for us to get rid of them. And this is a problem because only 1 out of 10 active galaxies produces a jet. So 9 out of 10, they don't. And so no matter what we do, the jets happen through that mechanism that I just described to you. It's too robust. So 20 years ago, people were celebrating creation of jets. And now for 20 years, we have been trying to get, at least I have been trying to get rid of them. And so this was my first attempt at getting rid of the jets. Because remember, if I go back, what are the 2 important ingredients for the jets to appear here? Well, one is rotation, omega, and the other one is we need to have the field line, so the flux like this sticking out from the black hole, right? So, okay, black holes, they rotate. We can't do anything about that. But what if we take away the magnetic flux? Maybe then the jets won't be there. So that's the experiment that I ran. So what you're looking at here is the initial conditions of our numerical experiment. So this is 100 times 100 gravitational radii on the side. So that's about 1 RG, 1 gravitational radius. That's the size of the black hole here. And this is a zoom in to the very, very center by a factor of 10. So this is 1,000 times 1,000 gravitational radii on the side. It's we're looking at the meat through a vertical slice through the black hole rotational axis. And what I show here is logarithm of density. So this is log of density. The top is 10 to the 2, and the bottom is 10 to the minus 8. So there is 10 orders of magnitude in this color bar. So this is nothing. That is everything. So what we're looking at here is a huge donut, much bigger than those that you have behind you. So this donut is, let's see, will be 100 times larger than this. So it probably ends just on Sheridan Road. Is it the right direction? I'm not sure. But anyway, it goes out really, really far. This is an equilibrium torus. So if I just let it run, nothing would happen. But then what we do, we insert toroidal magnetic field here because we don't want this field to be there. And we perturb the pressure here by like a few percent just so that the initial conditions are not exactly axisymmetric because otherwise nothing would happen. So no vertical magnetic field. Black hole is spinning 99% of the maximum spin. And the thickness of the disk, h over radius, is a quarter unity. So that's kind of a standard initial condition for the simulations. Now, what you're going to see is, in addition to the color, there will be also black lines, which show magnetic field lines in this vertical plane. Initially, there are none, but as you will see, they will appear, although I didn't want them to appear. So I pressed enter, I went on vacation, and I come back, and this is what I see. So you see, initially, there were no loops, and now they appear, these lines. Dashed lines show negative polarity magnetic flux in this plane. Black lines show positive polarity. So you see that there are opposing polarity loops appearing on large scales. And one of these loops runs away, somehow formed by some sort of dynamo, like the one that operates in the sun, perhaps. Apologies, the video is choppy. That's the zoom acting up here a little bit. But you see that this loop became so large that from the point of view of the black hole, it's as if that loop has always existed. So black hole is presented by this large scale of vertical magnetic flux that wasn't there to begin with, but the system self-consistently formed it. And that was a huge surprise. This was the first time this has ever been seen. And one other thing you will notice, maybe not so well here, is see the number of magnetic field lines keeps increasing. Number of magnetic field lines is proportional to magnetic flux that we have there. And eventually there's got to be a limit to how many field lines can get in there. And in fact, once the magnetic field becomes dynamically important, the outward pressure of the magnetic field becomes comparable to the gravity that keeps the gas around the black hole, then this magnetic field will start leaving the black hole. And in fact, that's something that we are about to see. I will not wait for it because I don't think it will be particularly dramatic given the frame rate. But what happens is if we were to plot as a function of time, mass accretion rate, that's the top panel, skip this one for now, and magnetic flux, then you see magnetic flux in the black hole, the blue one keeps increasing. Now let's look at this one. That's the ratio of jet power to accretion power. And you can see that this ratio, apart from this gap where the supercomputer Blue Waters helpfully deleted our data because it thought that we didn't need it, we get 150%. It means that the black hole spews out more energy than we put in. And this extra energy is coming from spinning the black hole down. That's the rotational energy extraction in action. And that only happens when the magnetic field is dynamically important. So when the power of the jets is of order of the power of accretion, we call this magnetically arrested disk state. And that's when the magnetic fields are dynamically important. So let's just take a sort of a step back and see what we just got. We started with no vertical magnetic field. The system generated enough vertical magnetic field such that it flooded the black hole. It became dynamically important and started to boss the gas around. And why we haven't seen it before is because we went to high enough resolutions to resolve the instabilities. And this is about a factor of 10 larger resolution in every dimension. So 1,000 times more cells than the regular simulation. And also the duration is about a factor of 10 longer. So, and this was 5 years ago. So next I will tell you what allowed us to make such a breakthrough in resolution and durations of the simulations.
On the movie, can you point out what the jet is?
Yeah. Oh, perfect. Thank you. The low density stuff here and there, above and below the black hole, these are the jets. Okay. Yeah. Thank you.
And there's like a higher density inside the jet.
This is
right.
This is we think it's purely numerical. There's almost no energy going out along the pole. The jets are hollow, but there is a polar axis that I know you've dealt with, but I still haven't understood how you dealt with the polar axis. So maybe now that I've given this talk over lunch, we'll figure it out. But it doesn't really affect anything. Good check.
Give us a flavor of what equations you're solving for the simulations.
Yeah, definitely. In one slide. Next slide. Good plan too. Yes.
I hope I'm not breaking your plan, but this is a semi-generic question about like observations and about your simulation. Is it inevitable that you get symmetric jets, that you have to have more or less equivalent north and south pole jets?
It's pretty generic that happens. Having said that, if you consider a less idealized system where it's not a torus, but like a real mess around that can happen on its own, just chaotically. Later on, I will show you a movie where the two jets don't have to behave exactly the same, but by and large, they seem to be tracking each other. If you have a large scale asymmetry, let's say more gas one hemisphere than the other, then that will naturally cause asymmetries. But other than that, typically we do see a rather symmetric behavior, but there are exceptions. Any other questions? Okay, so let me. I wanted to say a few things because Daniel published this exciting paper that dynamo in the sun might be happening due to similar instability called magnetorotational instability here in the accretion disk, which is what we think generates this large-scale magnetic flux. It's a really exciting connection. And in fact, after 5 years of trying, Jonathan Jagomin-Eit, who was a postdoc here and moved over to postdoc in Boulder, figured out what caused this large-scale magnetic flux to emerge in the simulation. It has been so frustrating. We see it right there in front of us, and yet we can't make sense of it because it's chaotic. It's turbulent. And so he was able to correlate things just with the right things in the right way, such that you get signal and the noise goes mostly away. And maybe you heard for the experts, alpha omega dynamo, where omega is the shear that converts this field into that field, vertical into toroidal, and alpha effect is what converts it back from the toroidal into vertical. And the nature of alpha effect has always been, we didn't know quite what it was. And so it turns out that it's not the standard alpha omega dynamo, but it's the one where alpha can randomly vary both in space and time. And so he can measure these alpha variations, and they indeed all over the place. So why it works, I don't know, but that's what works in this simulation. So I would love to see what happens in the sun. Are there any questions about this? Yeah.
Just one question about the jets. So the jets is like a low density region. I know it's like spitting out magnetic energy essentially. Is there some type of matter that's correlated with it? Is it also spitting out?
So that's a really good question. So like here, you see the jets when they're just starting out and breaking through whatever the envelope was. There is a matter that they kind of entrain and carry away with it. So we think that that's one way that the jets can accelerate matter. There may be other ways that we actually don't know. So how jets get mass loaded, it's a big question. And why are jets, mass loaded to the degree that, we see these Lorentz factors of around a few tens, at least in the context of supermassive black holes at the centers of galaxies? We have no idea. Why is it not a few million, or why is it not a few? And that's particularly upsetting because in other cases, like stars whose cores collapse and form a black hole, and that produces twin jets that pierce through the star, which we call them core collapse gamma ray bursts or collapsers. Those have been seen to make jets that are a few hundred, maybe even a few thousand in Lorentz factor. So why is there such a difference depending on the black hole scale? We don't have these answers. In fact, theoretically, I would have expected there are many more ways to mess this up in this really messy thing that's a death of a star than in a galaxy, but yet it's the opposite. Death of a star seems to produce faster outflows than inside of a galaxy. Right. So the planted question number 3, if I'm not losing the count. So this is a numerical simulation. I didn't write the equations, but I will write them on the board. The reason why we can do these things is because in 2014, my colleague Sarah Markov from University of Amsterdam reached out to me and said, "Hey, Sasha, I have a great student for you." This guy. He's a master's student and he is absolutely great. I know you were interested in accelerating your code with GPUs. Can you, would you be interested in taking him on? I'm like, no, I already have 5 students. As a postdoc, I had 5 students like all over the place. And I'm like, I can't take him on. And she's like, do it. You will not regret it. Oh boy, she was so right. So Matthew and I had a Skype call on my birthday in 2014. And I showed him the code and I paged down through the code and he's like, yeah, I understand that. No, wait, what is this? And he explains to me. Okay. All right, so basically we page down through the code and he's like, okay, I'm good. I'm like, wait, what do you mean? Let's talk about how you're going to convert it on GPUs. And he's like, no, I'm good. And then he disappears for a week. And I'm like, oh my God, I'm bad. I'm such a bad advisor. Like, of course, I can't let someone be on their own. Like the CUDA thing is complicated. The code is complicated. Numerical, like GR, curved space-time, relativistic plasmas. And then a week later, he's like, so in the conservation equation for energy, so we solve equations of motion in the conservative form, du, dt, and u is a vector of conserved quantities. In our case, it's 8 things. So conserved quantities will be conserved density, conserved energy, conserved momenta, P1, P2, B3, and flux densities, magnetic flux densities, B1, B2, B3. So these are the conserved quantities. All of them are conserved manifestly in ideal general relativistic MHD. And then this dudt will be equal to minus d, so let's do it this way, du, DUI, DFI, DXI, and then there could be a source term. Sorry, I'm getting confused right now. Why am I getting confused? Okay, it's just for one of them. Okay, there will be 3 directions, and then there will be and then there will be a source term. So these are directions. So this is a divergence of the flux, this is the source term, and this is a conserved quantity, and you can write exactly the same equation for each of these 8 quantities. That's literally the way we discretize them. I omitted some geometric factors, but it turns out that the curved spacetime we can easily absorb into geometric factors that can be hidden inside of the conserved quantity and the fluxes. That's basically what we do. At time t equals 0, we have a distribution of, let's say, density in every cell. And then at every time step, we figure out what is the flux between the individual cells. And then we move stuff around. Of course, we use the Godunov type approach, which is a shock capturing scheme. So we use a Riemann solver to tell us how much flux we have in between every cell. On top of this, you can add radiation physics, you can add neutrino physics, you can add other physics, which complies with the same sort of equations. So you can also add particles if you want. You can have radiation transport using Monte Carlo methods. The beauty of this is this really nicely transplants into GPUs, because GPUs, they have, let's say of order 100,000 threads. And so sort of my view of GPUs, it's like a CPU is like a 500 horsepower Ferrari, and a GPU is 500 horses. So if, let's say, you want to drive down to like a warm place, I don't know, where would you drive? Let's say San Diego. You want to go for a spring break, you want to drive to San Diego and enjoy the nice weather. Then what are the options? Well, you can either, and you want to move like a bunch of, I don't know, you want to take your couch because, you're renting a place. No, Santa Barbara, KATP at Santa Barbara. You want to move there and bring with you your couch, your favorite something, right? So you want to bring.
You don't need a couch. They already.
Okay. I mean, you're breaking my flow. Okay, fine. I don't know.
San Diego. Let's go back to San Diego.
Yes. So you're renting a cottage. You want to bring your furniture for whatever reason. So you could use the Ferrari to go back and forth, because like one chair, like it wouldn't even fit into like the trunk. I don't even know if there is a trunk in a Ferrari. So like you would try to attach it if it doesn't fall off, but you'll have to make a lot of trips. Whereas with 500 horses, you just, put one chair on one horse, table leg on another, and so on. And in one go, perhaps you can move your apartment. They will go slower, but they will get you there faster. So if you can break down your problem into individual pieces roughly equivalent in computational cost, then you're good to go. And so here we basically give one cell per thread. And then if there are more cells than threads, then each thread of the GPU is kept busy, and then we can get a pretty good efficiency out of it. So it's a team effort. Lots of people have been working on there. Like Valeria, for instance, was an undergrad here, went to PhD in Columbia last year. Nick Kaz is a grad student who is moving over to PCTS, Princeton Center for Theoretical Science, next year. So 15 years after I was there, Nick is going to take a fellowship there. So the code uses message-person interface for parallelization between different nodes, OpenMP on the node if there are multiple GPUs, CUDA and NVLink GPU direct, and can also now it can use HIP, which is for AMD, or OpenCL, which is good for Intel GPUs like in Aurora. Those GPUs are not very fast, but since they're there, we can use them. So come talk to me if you're interested. Yes.
Are the exabyte like cylindrical coordinates, or do you work in Cartesian coordinates?
The beauty of this is these coordinates, xi, they can be anything. You basically you can parameterize a metric around the black hole in any coordinates you want, as long as you can write a metric in your coordinates. As long as the coordinates are smooth, the code can take it. Okay.
And then what are your boundary conditions?
Okay, so the boundary conditions. I'm thinking whether I have something better. Let me show you here. So this is the internal coordinates for a simple axisymmetric torus accretion problem. Except this is theta angle in radians from 0 to pi, and this is log radius, log base 10 in radius, going from roughly 0 to 3. So the radius goes from 1 gravitational radius roughly to 10 to the 3 gravitational radii. So it's 3 orders of magnitude in distance. This is the bottom pole. That is the top pole. This is the black hole, and this is the outside. On the black hole, the coordinates, they go inside the event horizon. And then inside the event horizon, we absorb everything that falls in. We use outflow or absorbing boundary conditions. And what exactly we do there doesn't matter, because equations prevent the signals from escaping from the inner boundary because it's inside the event horizon. And outside, we place this boundary so far away that whatever happens here doesn't matter. But it's not critical anyway, because all of the stuff that's crossing this boundary is typically going out, and we just absorb it. Here, transmissive boundary.
Like a damping layer. And you have a damping layer and the outflow, is that correct?
We don't have anything special, like in terms of damping layers. I don't think that our technology is far enough. way to do that, but we find we don't need this. So what we do is if we have, let's say, this is my active domain, and then there are a couple of, ghost cells. So this is active and this is ghost. We just copy all of the active values to the ghost cells. And that turns out to be good enough, both at the outer boundary and at the inner boundary. Moreover, even if there were a reflection, we place it so far away that the time for the signals to come back would be longer than the simulation duration time anyway.
So you effectively stop the simulation if you see or get any reflections from the boundary.
Ideally, that's what we would do in practice. We find no difference when we hit the boundary or not. There is really, it's because everything is supersonic. Again, the equations prevent the signals from propagating back. So equations help us both on the inner boundary because you would have to move fast than the speed of light to get out, and at the outer boundary because you would have to move faster than the speed of sound or magnetosonic speed, fast magnetosonic speed to go back. Make sense?
So yeah, seems like you are adjusting the cell size as the dynamics go.
Yeah, thank you.
I don't understand the reason for the smaller box size in the top one.
Oh, yeah. So this is just a test.
Okay.
Yeah. We wanted to, because we realized that there is no tests of, again, maybe I should talk to you. I'm sure that there is, but in astronomy, the only way we test adaptive meshes, what we see here, this is like adaptive mesh where we said we will have a wave that propagates, just as it's an entropy wave, I think. This is density. And we want to make sure that the system converges at the right order and the error actually goes down when we refine the central block as opposed to not. So here, this is also just a test to see and illustrate that adaptive meshes are working. And this is one of the cool features, not just adaptive meshes in space, but also adaptive meshes in time. So this block, for instance, will have a time step that's much larger than that block because the size is much bigger. And so we can extend this outer boundary essentially for free for us because those blocks weigh much less. So this plus the GPU acceleration enables really big simulations. And then if you couple that with huge Department of Energy allocations like on Aurora, Summit, and so on, you literally can have access to about, I would say, 1,000 times more computational time than if we used our codes before this one using the CPU. So that's how we can get to those high resolutions. Are there any questions?
So is your program with these different time steps, I suppose you have to do some interpolation, is it second order? What is the order of action?
It's second order, yes. Second order, we find it's totally enough for us. Yeah.
Are you doing a mixture of implicit and explicit time stepping here, or is it?
For ideal geometry, we don't need to. For radiation, we have to do semi-implicit schemes that treat radiation part of the time step implicitly, because otherwise it would be an unstable situation.
So for stability, are you just monitoring CFL conditions?
Correct.
Looking at the sizes of the boxes.
Exactly.
So you're talking about the weighting.
Yeah, we use the current condition, and in every block, we have our own current condition, and the time steps between two neighboring blocks can change by at most by exactly a factor of 2 is 1 a factor of 2. So we never allow the time step to jump by more than a factor of 2, just like the resolution. And so here, if we have these 4 blocks of the same size, then this one can have the time step that is factor of 2, 4, 8 times larger than here. But in practice, we have more blocks in radius, so typically. But even if this is 1/8 of this, this is free for us. Make sense? Yeah. Okay. Cool. So anyway, cool things. Let me show you. I have about 10 minutes, right? So there will be lots of movies right now. So this is what I promised. This is something that starts ridiculously simple and becomes ridiculously complicated. This is my favorite kind of experiment where I put in very little, highly controllable initial conditions, and it becomes a mess that looks real-ish to me, to my eyes. So this is a black hole there. You don't even see it. This is 1,000 times bigger than the black hole, and the red thing is empty. So red here in this movie will be almost nothing. Black is uniform density outside. So we have uniform density, cut out a hole in uniform density. There's no rotation outside of this hole, but there's a rotation of the black hole. And then we insert vertical field here. Why do I insert vertical field? Is because this field, once it gets in the black hole, will produce a jet. I'm fine with that here. What sets the size of this, and what is this RB? B stands for Bondi radius. This radius is set by the force balance between gravity and thermal pressure of the gas. So the higher the temperature, the smaller this hole will be. Basically, outside of Bondi radius, the pressure forces are strong enough to counteract gravity. Gravity is not felt. Inside this radius, gravity is the boss. Okay? So this is basically the radius from which the black hole can pull the gas. This is the sphere of influence of the black hole. In reality, it's about 3 orders of magnitude larger, 10 to the 6 gravitational radii, but we can't handle such a large scale separation. So we reduce it down to 10 to the 3 and hope that the results won't be too different. And then the idea was, when I was writing proposals, we will vary this scale separation as a parameter in the problem and see if we can get some scalings. And when I was writing the proposal, I didn't believe it will work out. It works out better than I could have ever expected. So enough talk. Let's run the simulation. So the hole closes on the free fall time scale. Magnetic fields get in the black hole, produce jets, and then fall apart. And then it tries to burp a little bit, but the jets never get out of the sphere of influence of the black hole. So let me play it once again. The jets form. They get out very far from this influence of the black hole sphere, and then everything falls apart. So this was pretty remarkable. We started with something that was completely axisymmetric, and we ended up with something that's a complete mess. And the only thing we did to break the symmetry is to add this few percent pressure perturbations outside. So one more time. So jets launch, and then they become unstable, they fall apart, and then they still launch, but they launch kind of in different directions. Yes.
You cross the rotation. So in your simulation, you have no rotation? If you go on the previous slide.
No rotation outside here. There's no rotation of the ambient medium, zero angular momentum.
Okay, but the black hole is
spinning. Black hole is spinning. That's why there is rotation.
Where is the uniform magnetic field coming from?
By hand. This is our initial conditions.
Okay.
Yes.
But in reality?
In reality, we think that's probably more likely it will be azimuthal. If this is a supermassive black hole, we see microgas magnetic field strength in the interstellar medium. And microgauss, if you bring it down to the black hole, it will be pretty strong, just because of magnetic flux freezing. So here we assume that it's not exactly azimuthal. There is some vertical component. We say, what happens if we put some vertical component? So this is like, what I wanted is minimum free parameters. So one free parameter is the strength of the magnetic field. The other free parameter is the distance. And the third free parameter would be the angular momentum of the ambient medium, which is set to 0 here. And the other parameter is the black hole spin. Of course, I could then tilt these things, but I don't want to get there. This is the very first exploration. Nobody has ever done this because everybody tried to deal with tori. But torus is really, really hard thing to analyze because I don't know, what do you expect at 0 level when I put a torus? I don't know. 0 level, if there is no magnetic field, 0 mass accretion rate, but that's not interesting. Whereas if I have a spherically symmetric gas, I have a spherical Bondi solution that gives me m dot. And mass accretion rate, I can compare everything against that. And that is a game changer. Such a simple little thing allows us to understand the physics of the system. I would say not understand, but reveal. We still don't understand what's going on. But hopefully there is an understanding that will come out of this. Okay, one last time. There might not be too many more movies, so I will need to wrap up.
What's the role of the fluctuations in density? If you say if there are no fluctuations, then nothing happens, right? Because you don't have, unless, maybe through numerical errors, there will be some emerging, but you could imagine that you make them so tiny. Is there kind of a delay in the time for things to occur? What is...
The instabilities that drive this, it's Rayleigh-Taylor instabilities, magnetic Rayleigh-Taylor instabilities, Kelvin-Helmholtz, whatever you can name it, and maybe most importantly, magnetorotational instability, which exponentially grows. It grows exponentially. So as long as you break axisymmetry in some way, doesn't matter at what level pretty much, even if you break it at machine precision level, 10⁻⁻15 or something like this, it will end up be looking almost exactly like this, because any tiny perturbation will be amplified exponentially and get to the order of unity. Yeah, the reason we do it 1% is because we want to be dominated by our perturbation rather than the numerics. But we have verified is if we give 0 perturbations, then by accident, I forgot once to include them. What we found is the whole system behaved exactly axisymmetrically because the code doesn't want to break the symmetry.
Right, because you have error corrections in there, and so you are also suppressing some of the numerical things, I would imagine.
Let's talk about this offline. I'm not sure I fully followed the question. In this case, though, because we don't want jets to be interacting with the polar axis, we tilt our spherical polar coordinates such that our polar axis goes sideways. It turns out that rotation through the polar axis of the disk is much easier to handle than jets that are highly magnetized and really fragile to go through the polar axis. So just an aside. All right, so the bad, the mad, and the rad. Let me explain what that is. So the mad is that mad state. Initially, the magnetic flux accumulates in the black hole, and the stable jet that you see, which was going up and down, that was dynamically important magnetic fields pushing the gas out. They were strong enough to punch the hole through. In fact, you need to be mad or half mad or so in terms of magnetic field strength to even be able to drill a hole through the lid, it turns out. So mad is strong enough. And what's cool is that the black hole gets only about 2% of that expectation, the Bondi expectation of a mass accretion rate. And that is consistent with recent observations of about 1% or so of the gas reaching the black hole. So it is the jets that are able to somehow suppress the infall of the gas. Now, why do I say though is because the bad is when the jets are falling apart, we call it barely a disk. Because we put so little angular momentum in the system, then the only angular momentum that comes is from the rotation of the black hole that drags the space-time. And that kind of pulls the angular momentum out of the black hole and creates a disk. And that's when the jets can form. If for whatever reason, the angular momentum of that disk gets eaten and new one doesn't come out, the jets fall apart. The disk starts to precess really rapidly because of the angular momentum being so small. And the mass accretion rate on the black hole can go up as high as 10% of the expectation. And finally, the rad is rocking accretion disk. This is when the jets have been so strong, they injected so much turbulence into the ambient medium that our zero angular momentum initial condition has gained angular momentum, but chaotic. And so there are different pieces of gas falling in with different orientations. And so there is a tiny disk that's continuously getting reoriented, it's taking the jets with it. And so these jets, you see these are the jets. They're completely tangled, they're falling apart. That's why the jets can't make out of the central region. In this case, however, because the jets are kind of covering large fraction of the sphere, you can also bring down mass accretion rate as well. So you can either bring down by pushing the gas with strong magnetic fields, or weaker magnetic fields can sort of mess it up if it goes all over the place. And you will tell me, Sasha, but this all is one simulation. We know that it's chaotic. What if you run it the second time? Or if you were to add rotation to the ambient medium? Because sure enough, this thing and that thing will never happen because you'll have huge amount of angular momentum. So only this is possible. I agree with you, fully agree with you. Except that the simulations don't agree with that. So these are simulations with angular momentum, circulation radius of 30 gravitational radii, which means angular momentum is such that it corresponds to Keplerian angular momentum of 30 gravitational radii. Anyway, it doesn't really matter the details, but now there's angular momentum. And we vary that parameter, which is the scale separation of the problem Bondi radius, to the gravitational radius between 100 and 10,000. This is beyond our capacity right now. We can only get it out to 3,000. And what that means is that at such a huge scale separation, for us, it's like the largest scale separation ever. We beat it by a factor of 30, which was previously the largest one. We get complete steady state out to that radius. So let me give you an example. For instance, for 100 gravitational radii, we have m dot over m dot Bondi of about 10%. So 9 out of 10 grams that we expect the black hole to pull in from the sphere of influence gets ejected. Only one gets accreted. Let's increase this to 300, the scale separation to 300. Then you see the fraction of gas reaching the black hole goes down to maybe 2, 3, 4 to 5%. That is the mad state. That is when the jet is pointing up and down. It's stable. And then when we get to red state, that state that was on the right, the mass accretion rate is higher. And then it goes to mad state again, goes back to red state, goes to mad state, red state, mad, red, mad, red, mad. That had angular momentum. Now let's go to 1,000. Mad state at the level of about 1 to 2%. Red state. So here the jet is pointing like this, really happy, and then it messes things up enough, injects enough of weirdness that the regular rotation that we started with gets disrupted. And by the time that disruption gets to the black hole, it doesn't have a disk anymore in the regular sense. It's completely messed up. And that's why the jet starts to go around and around and go crazy. So that means that red state is generic. One thing that I want to mention here is this duration here. I have to count zeros myself. Typical duration of the simulation is about this, 100 times shorter. So this is 1.5 million dynamical times. This is completely ridiculous. When people see this at specialized conferences, they think we made a typo. Okay, this is not a typo. Iris ran the simulation for months in order to get here. And this one is still running. What do we get out of this? I promised you that there will be perfect, like really exciting scaling. This is m dot as the function of the expectation, as a function of, and versus the scale separation. And you see that there is a single power law. As we vary the separation, the fraction of gas reaching the black hole behaves as a power law. And the accuracy of this power law is minus 0.66 plus minus 0.01. This is ridiculous. You can see it, you can also see the same power law in the every simulation itself. That's how the mass accretion rate varies, the one that goes to the black hole. So it's not the only place where we measure this. So I think this is all the time that I have, but I want to sort of give you a takeaway of how we set up simulations in an idealized system, and then we get something that's very complicated, and then we can get the scalings, and that can allow us to, generalize this to the more realistic systems. Thank you so much.
The last 2 points on the scaling, were they real or not? Sorry.
No, they were not real. That's a good point. Let me go back.
Because you have barely a decade of data, so it's kind of a bit of a, claiming power law.
Yeah. So no, I agree with you. I'm not showing the whole. So what happens is that at first, each point starts out here and then slowly lands on this. And then our simulation is located right now out of here. And then we said this is the factor that we saw every other point start out and then slowly go up. So we expect this one to go up here, but this point is not a data point. So we only have 4 data points. But then if you are in doubt, as we were, we can actually plot the ingoing mass accretion rate as a function of distance. And that is what I show here. And this is pretty much one single power law, and these are at different times. And as you go to larger and larger time scales, this becomes a better and better power law. This is the Bondi radius. This is the black hole radius. And this power law, it's 0.67 plus minus 0.02. And I think this is a 3 sigma error bar. So because we have 3 orders of magnitude, it's exactly the same power law. Not surprisingly, because, this is our expectation, and then it goes down as a power law, goes to the black holes. If we have more orders of magnitude, then there will be less and less gas reaching because it's one power law that's going down. And this is the other thing, this is kind of the money plot as well. This is the net mass accretion rate as a function of distance. And what does it mean? If we have steady state, it means that mass doesn't get destroyed or created or accumulated anywhere. And so that means that net mass accretion rate should be constant, and it is exactly constant over 3 orders of magnitude, which is the very first time that has ever been possible over so many orders of magnitude, which means we have truly reached steady state. Does that answer the question?
I think unfortunately we're out of time. I mean, you said that you wanted to be interactive, and maybe it was more interactive than you
That's
were
perfect.
anticipating.
No,
So
I mean, lots of questions were going along the way, and I loved it. So thank you so much. You're a fantastic audience. I'm really happy to be here. Thank you.
and thank you, Sasha.
Oh, one question online. 1 sec. Thank you.
That was not meant to be everybody has to. Dave had a question online.
Oh,
I was letting Sasha
The one you already
know.
adjust.
Okay,
So,
okay.
why is the power law relation breaking? Can you, if you can speak up, Yanis, what do you mean by breaking? So like here,
I wonder, like
In your plot, it looks like the linear relationship is starting to get out of whack.
This one, the power law outside of large distances.
Yes.
Oh yeah.
So I was wondering what are the mechanisms that will take you away from the scaling regime?
Yeah, it's because if you're talking about this large scales, it's because it's outside of the equilibrium radius. We need to run it for longer and longer in order for see this m dot. As we go from shorter scales to longer scales to even longer scales, it becomes more and more constant, and then the power law extends out to larger radius. So that's what we need. Just run it for longer. Does that answer the question?
Yes, thank you.
Perfect. Thank you so much, everyone.
Thank you.